we had a lot of discussions with Emmanuel about how to implement this continuous approach that you will see as a conclusion of this presentation, how to continuously run a Simba model with the insertion of like Python-based script that can influence actually the behavior of the simulation, with the goal of having quite didactic result for both like learning about Python, learning about Simba modeling, and especially about how to model MVDC microgrids featuring solid-state transformers. So this actually kind of relates also to the presentation by Khaled Sailan, because like you may find in the shared models like a quite detailed model of a solid-state transformer based, a dual active bridge-based solid-state transformer. So a few words about me. I've been like, I'm now working with Hitachi, but I was with various places that are both industrial research places. And now with Hitachi, I'm working on SSTs, among others, and also static frequency converters. As a full tutorial outline, I go with an introduction, system level models where I show some elementary DAB-based SSTs. I will skip a lot of them. We will not have the time to go through all of it, but I will jump to the end to see like this continuous run approach. That was really actually a quite fun exercise that we had for being able to sort of like have a very basic graphic user interface that is based on Python running a Simba model. So you will find here like all the libraries that I'm using for running Python and the models, calling the models and like displaying the results. This you can get in the link that got soon, and all the models will be available here. You will see you can have a README. You can like, check inside a model that is a JSON Simba model type file, and all the Python scripts that will allow to reach the models that I will show. I will not show everything, but yeah. So also some references. Let's start with just, I will spend some few time on like the elementary DAB-based cell to show like just the philosophy of this system level approach modeling. Just a few words that we are basing our research on the real case. With Hitachi Energy, we had the we have the ambition of commercializing a megawatt range dual active bridge converter. So this is our basis for being able to compare and to validate our model. So let's start with the grid. What is a grid? The voltage source, and the impedance is a current source that emulates the DC grid impedance as see from the point of common coupling. So it starts from this, and with this idea, we developed the whole SST model. We have a voltage source as a capacitor for the capacitors, a current source for each side of the MFT, a current controller, a voltage controller in a cascaded fashion. That's quite typical. You will find this in most of the references about dual active bridge. In Simba, so as you can see, you have a hint of which Python script to run. We have those sources, and in green, as you may know, like the control side, or for example here, the implementation of the grid impedance as seen from the point of common coupling. This is the whole strategy, basic strategy that will bring us to run this model that will implement the dynamics of an SST as seen from its terminals. If we run it, okay, it has been demonstrated earlier that we can run Python scripts with parameter sweep. Here we have various dynamics, whether we want some slow or some fast dynamics. And how do we validate this model? You can run this one Python scripts where I have actually implemented a detailed model of a dual active bridge with a controller and a sampler and a modulator, as it would have been implemented in an FPGA with a 20 nanosecond time step. As you can see here with the switching model, you have load current that is pulsed, and the RMS value of this pulsed value give the green value that is quite similar to the red one, which is implementing the average model. As we can see here, as a result, on the DC bus that we are trying to control with the SST, we are quite similar with the switching model on the average model. As a conclusion, we have one SST that has a pretty fair dynamics as seen from its terminals. Like, we are not talking about what's happening inside, but this will help us to build a series parallel connection and to be able to simulate a system with a lot of DAB-based SSTs. Here, for example, an example of series and parallel connection of SST. One can ask, like, how can we parallel connect voltage sources? This is not possible. Well, there is a way we can do it by considering intermediate point of common coupling and those current sources that would implement the cable model that is connecting all those SSTs. A cable model as resistor and inductor. So this helps us to be able to distribute and also to have to test accurate current balancing in this kind of configuration that we call IPOS, input parallel output series. This allowed us to demonstrate that we can have asymmetric loading on the system level and still be able to accurately control each of the transmitted power. As you can see in Simba, the system becomes more and more complex with a lot of subsystems. There we had a lot of questions and ideas. How possibly use a reference subsystem, for example, how to be able to build our own libraries. This is still ongoing. And as you can see, with asymmetric loading on the MVDC side, we have a very good behavior of our multi-cell input parallel output series SST active frontend. We can also check what's happening on each of the cells. We have some asymmetries. It makes a very nice curves that were generated in Python. So let's jump again in the presentation, and what we want to do is a full MVDC microgrid with a lot of with a MVDC backbone connecting the LVDC grid with actually a lot of SSTs. Let's see that this group has 10 DABs, this one has 10 DABs. All this is reached with one SST model, which is this 1 megawatt SST model we want to implement everywhere with parallel and series connection, modular fashion, to be able to run this kind of system. So we have a lot of current voltage sources, a lot of those elementary SST cells all put together. Here 30 are used and independently run this model. If we run, see we jumped a bit, if you have questions about intermediate stages, then you can refer to the presentation that was shared. So the full DC microgrid is run here in Simba. Here we have an example of, for example, like a point of common coupling between an active front end and the so-called passive front ends. Here we have a way of controlling the active front end controls the MVDC backbone, and the others are simply like current sources. So we tried a given a scenario running over several hours with sun coming in and out, with cars getting charged or not, with the best system like supporting the grid when we have no more sun. So this was an element like exemplary scenario that we tried just to show the possibilities of this setup. Let's talk about an interesting project we had in collaboration with the University of Applied Science in Yverdon in Switzerland, with a student that implemented in Python a so-called continuous run approach, by running at a pseudo 1 microsecond sampling rate with the snapshot principle. So we have the same microgrid that showed before, that is run with the so-called energy management system, and we can change the parameters and get the plots. So this Python script is running at the so-called pseudo 1 millisecond sampling rate, and would possibly be able to implement automated energy management features, AI-based, whatever, anything that can be written in Python. So it looks a bit like this. You can run it, you can try it. And when you get it from my GitHub, you can run the number 7 examples, and it will open a window, and you should, in theory, be able to change here some values and update the parameters and have, it's quite slow because there's a lot of it. It's a big simulation, and it's maybe not the most optimized way of running this, but we have actually a graphic user interface that allows us to live interact with the Simba model run continuously. Yes, so that's what we did. More or less a didactic tool for simulating complex DC power systems that still implement SST dynamics as seen from its terminals, and also to present an approach for DC power system study. And like we can imagine as the next steps, like modeling troop controls for MVDC, implement hardware and software protection schemes, if that's what is interesting for us, like how to protect on the MVDC backbone side, and possibly implement some AI-related Python toolboxes that could be applicable to control power systems. Yes, that's it. Here we have a link. You can send me an email if you have questions, or like get the models. I think you might find another Simba model there that I did previously with an active front end control handling asymmetries. Yes, that's it. We have 1 minute for questions.
Thanks a lot, Daniel. Yes, we have a little bit of time for questions. There is one from Marcelo if you want to answer it.
Wait, I will stop sharing.